Okay, so in the first video we got to the idea of defining productivity, being just think about a Turing machine that runs on a blank tape and how much does it leave, and if it leaves a unary number on the tape, that'll be its productivity. And the busy Beaver function is the highest productivity we can achieve with the most clever end-state machine. All right, and 3 symbols. Or you could use more symbols if you want, but you got to fix a number of symbols. And we saw that with 10 states we could easily get the number 10 eyes onto the tape. So there's probably a more clever machine. B of n is going to be the productivity of that most clever machine. And we also saw, as a step towards increasing our cleverness, we also saw that with 3 states we could double something. So here I could have a machine, this machine we saw would write 3 eyes onto the tape, and then when it got done it would go to the doubler, and then we could double, and then if we wanted we could add 3 more states and go to another doubler, like that. Okay? So that kind of thinking will allow us to start to get exponential looking behavior out of this thing. However, right now we want to start thinking a little bit about the B function as whether or not it's mathematically, is the thing actually well defined? I mean, and we've been thinking in the previous video, partially like programmers. Here's a machine with these many states, we write these many symbols, we're writing little Turing machine programs to do stuff. Mathematical computations, very simple mathematical computations. But we're going to keep thinking about it as programmers, but also as mathematicians. And the question I want to ask right now is B actually well defined? So for any given number n, is there really a B value? And the answer to this is going to involve proving that there actually are a finite number of Turing machines of a specific size. So if I want to think about what's the productivity of the most clever 10-state machine, I'll have to start by showing that there are only so many 10-state machines. There's not an infinite number of them. So think about each machine, a n, as having n states times, okay, in this case it's 3 symbols, okay, remember we're working with only 3 symbols. So for the example, this was our machine that writes 3 eyes and halts. Well, in theory, we have 3 states. We have 2 symbols, which were blank and I. We started on a blank state tape, and we only ended up using these 3 states. But if there were any eyes on the tape, we'd end up doing some of these states too, and they just move over onto the left. And then they'll add a few more eyes onto whatever's there. So this has what? This has 3 states. Each state can look at each symbol. So we have 6. Okay? Times 2 symbols. All right, the symbols are blank and I equals 6 rules. So any Turing machine we write with 3 states and 2 symbols has 6 rules. Some of them we might not reach for some things, but it has 6 rules. Okay? So think of that as the number of lines in your program. Okay? Now how many ways are there to write each line? Well, let's just imagine over here just the first rule, Q0 and blank. Okay. All right. Okay. 0, comma, blank. And it will go to a new symbol, right? Two possibilities, or we have three symbols or whatever. All right. And a new state, or movement. Size of the alphabet. And a new state. Okay. So that could be, all right, over here we had Q0 and blank, wrote an I. It could write a blank or an I or a J if we got J's. It could move left, right, or not move. It could go to Q1, Q2, or Q0. We could go back to Q0 or we could halt, okay? So for this doubling machine, 3 possible, or 2, 3, okay. All right, 4 new states. Okay. And 3 movements. So 2 times 4 equals what? 24, right? Okay, so each slot each of the 6 rules has 24 different ways to write it. So 24 times 24 times 4 equals 24 to the 6th with 3 states and 2 symbols. Okay, so there are 24 possible Turing machines that we could have written of with 2 symbols and 3 states. All right, each Turing machine has 6 rules. Each rule has 24 different ways to write it. All right, and most of those Turing machine rules won't be reached, and I mean, your average running of the program might not actually reach a particular rule, but that's okay. All right, so that is really important to this question over here. Okay, so total number of TMs times n is what? It's the number of states, n times 3, assuming alphabet, n times 3, and that's the number of rules we had, and we had n times 3 times n plus 1. So that is new states, new symbols, and head movement. Okay. Okay, let's get that, the size of the alphabet. Okay. Okay, so there's that many Turing machines. And now notice back here that the way these Turing machines work is that there are really only two possibilities. They halt or they don't halt. At any given cycle, where we have a symbol, we have a state, we have a rule. Okay, if we omit a rule, maybe the darn thing halts. We can define that however we want. But there really is not a lot of possibilities for the final outcome. Either it halts or it runs forever. Okay? There's no probabilistic, there's no runs faster and faster and does a Zeno thing of converging. It just cycles, every step, all right? If there's a rule for it or not. If there's not a rule for it, it'll halt. If there is, it has something to do, it steps. So the point being that each of these large numbers of Turing machines has an actual defined result. All right, and if that that result is a unary number, okay, then that's the productivity of that machine. So each of these halt, leave a string on the tape, a unary, okay, end-state machines. There is a highest productivity. All right. There might be several which are equally clever, but there is a highest productivity. So I claim that B is a well-defined function. You give me a number, all right, 8 states. I will assign homework. My students will run out and try and figure out the most clever 8-state machine. I might need a lot of students for this because there's a lot of possible machines, but they will be searching and they'll try to find what's the most clever 8-state machine, and there's only a finite number of them, so there is somewhere a most clever 8-state machine, and its productivity is B of 8. So that's important property of B.